Right. The fifth variable or situation that can affect the size of your R value is something called restriction of range, which is also known as univariate selection. All right, and it's very important. So don't ignore this part of the lecture. Okay. All right. Let's start by looking over here at the scatter plot. What I want you to do is I want you to look at all the dots in the scatter plot. So totally ignore the lines I've drawn around them, okay? Just look at the dots. If you were to just look at the dots, you would say, oh, there's a pretty strong relationship here, right? Just look at the dots, nothing else. Okay, I can draw a line and there's some scatter away from the line, but it's not that bad. I would say there is a pretty strong relationship between X and Y. All right. Now, to see that, though, you had to look at the full range of X and the full range of Y. Now, what I want you to do is I want you to zoom in, and I only want you to look at these values of X. So this now is in your blind spot. You don't see it because you've zoomed in on a very narrow range of X. Okay. And when you do that, what are you going to be able to see? Only these dots. And these dots here, because you've zoomed in so closely, you're not including that much data. There's not much opportunity here to see a relationship. All right. So had you included the full range of X, you would have included the full range of Y, and you would have seen there's a relationship. But if you zoom in too closely, that relationship may disappear. All right. Now, this is what typically happens when you restrict your range. When you either just look at a narrow range on X or a narrow range on Y, either way, when you zoom in like that, you are probably going to get a weaker relationship. But weird things happen. Here, if we look at all the values, okay, look at all these scatter plot dots on the scatter plot, we would say, oh, there's not much there, right? Actually, there could be a curvy linear relationship going on. Let's pretend there's another dot here, all right, just for argument's sake, so that way we can say, there's nothing going on. Now, that's if we look at all of X, which means we're also looking at all of Y. But what if we zoom in? We're only going to look at a restricted range of X values. All of a sudden, okay, so this is all in your blind spot. All of a sudden, now it's like, oh, there is a relationship between X and Y. All right? Because this is all you can see, so you would conclude that there's a pretty strong relationship between X and Y. But just note that this situation doesn't usually happen. This one is far more common. Now, I have an analogy. All right. First of all, let me just reinforce this. So more often than not, if we look at a very narrow range of values for X or Y, R will go down. So this is what we're going to see. Now I have an analogy for you. So you've heard about the expression, you can't see the forest for the tree. Is that right? Yeah. You can't see the forest for the tree. What we're saying is that you're too close. All right. You're butt up, get the butt of the tree, get that pun? You're butt up against the tree and all you see is the tree, can't see the forest. So to help reinforce this point, I'm going to come back to this. All right. This just says that if you want to know if there's a relationship between X and Y, you should test a large range of values for X and Y, and that gives you the best chance of finding a relationship. Sorry, I forgot that's what happens when you don't have a split screen. All right, let's go back to the can't see the forest for the tree analogy and show you what can happen. This is why if we zoom in too close, we might miss the relationship. So here is a beautiful forest, right? You can see the forest, no problem. Now, I want you to start walking towards that tree in the very front. Walk some more, a little closer, not there yet. Closer still. One more. Up. Okay, your nose is on the tree. Can you see the forest? No. The forest is there, you just can't see it. All right? This is a good analogy for restriction of range or univariate selection. If we zoom in either on X or Y, we're getting too close. There could be a relationship there, but we won't see it. All right? You can't see the forest for the tree. All right. So, whenever possible, this is what I skipped over before, whenever possible, choose what or who to observe in such a way as to maximize the range of values for X and Y. So you want a wide range of values for X and a wide range of values for Y. So let me give you an example. Let's say we want to know whether or not GRE scores are correlated with GPA in graduate school. Okay, so GRE, graduate record exam, it's like the SAT or the ACT, except it's what undergraduates take as part of a requirement for entry into graduate school. And the higher your GPA, the more likely you are to be accepted into graduate school. Okay, your GRE scores. But we might want to, say, well, do they predict, is there any relationship between GRE scores and GPA? Is it true that the higher your GRE, the higher your graduate school GPA is going to be? The answer, because these studies have been done, and the answer is no. There's actually a very, very weak relationship between GRE scores and graduate school GPA. So we have to now take a step back. Here's a little hint. Take a step back. What's wrong with this picture? You might think it should make sense, right? The higher your GRE score, the better your GPA in graduate school. Why aren't we seeing this? Take a step back. Zoom out, right? What we're seeing is a problem with restriction of range. All right? We want to know if there's a relationship between GRE scores and graduate school GPA. Now, if we were to admit everybody into graduate school, regardless of their GRE scores, so we would have some very low GRE scores, we'd have moderate, and we would have high. If that were true, then we probably would see a relationship like this. All right. And it would probably be true that if you score really, really horrible on the GRE, your graduate school GPA would probably not be very good as well. All right. Now, that's probably going to be the case. There will be exceptions, but for the most part, we have every reason to believe that you score low on the GRE, you're going to score low on your graduate school GPA. You're going to have a low GPA. But we don't do this. Graduate schools don't typically accept anybody with a very low GRE score. They only take the top tier for the most part. So what they're doing is they're zooming in on the x-axis. And again, what happens when we zoom in on the x-axis? We can't see this, right? We can't see the forest for the tree. We've zoomed in, and then we're looking at GPA of people who are already getting very, very high GRE scores. These are the, quote unquote, best of the best. Not that having a good GRE score means you're a better person. It just means you scored higher on the GRE. So best of the best GRE scores, they are probably all going to get very high graduate school GPAs. All right. So if we really wanted to know, is there a relationship between GRE scores and graduate school GPA, we would have to admit people into graduate school who scored low, medium, and high on the GRE, and then we'd have a better chance of discovering the relationship. And we're out of time.